Okay, so today we're going to discuss the chapter 10, which is the gas chapter. Remember at the beginning of the semester, as we go through chapter 1, we said there are three states of matter. We have a solid, liquid, and gas. So when we look at the microscopic overview of these matters, so we realize that the solid, those particles are very much close packed to each other. They are not allowed to move. They are very much restrained and packed in the three-dimensional network. Let's just focus on the kinetic point of view, kinetic energy point of view of the particle. We realize that a particle cannot be moved, so it doesn't have any motion. Since it doesn't have motion, it doesn't have kinetic energy. As for liquid, those molecules now, or particles now, can move around, but they are very much restrained because, again, those particles still close contact each other, or close packed each other. Although they can move, they cannot move very fast, and they are limited and restrained in certain area, or in certain space. To this sense, although particles gain a certain degree of kinetic energy, but not much. So from this point of view, we realize liquid has a higher energy than the solid because liquid, in addition to whatever the energy the solid has, now it has more kinetic energy. Gas is totally different. Those gas particles are no longer restrained in a certain space. So they can fly freely. Instead of move, they fly, which means they move in a very high speed. How fast it is, I like to put it into the scale like it's going to fly like 4 or 5 times faster than the jumbo jet. So this is how fast those gas particles can move. And one other thing I'd like to point out here is those particles stay very far away from each other, about 1,000 times of their sizes. Let me put it in a real example. If I stand in a certain area, the next person I can see, or I can call neighbor, is about a mile away from me. So this is just how far away those gas particles are from each other. As we know, those gas particles fly around very fast, and they stay away very far away from each other. As a result, those particles, gas particles, fill the entire space. Remember, as we talk about the kinetic energy point of view of these particles, it's easier for us to realize that gas is the most energetic state, while the solid is the least one. So, in this chapter, we focus on gas. If you're interested in the liquid or solid, this is something that we're going to discuss in the chemistry major for senior 4 years later. Because this perspective or the characteristic about a gas, which is far away from each other between the gas particles, so we can draw some properties of the gas. For example, gas particles are very far away from each other, so that means if we put the pressure around those gas particles to squeeze them into the shorter distance, sure, we can do that. So gas can be compressed, and the gas can be contracted. So that means if we slow down the gas particles by dropping the temperature, in this way, gas particles intend to get closer to each other. Eventually, as temperature drops down too low, it becomes liquid. So the volume of gas can be compressed or contracted by the drop of the temperature. Of course, there are other properties that also related to just how far apart those gas particles are among each other. Like gas particles has low density, because for the unit of volume, there are not much gas particles around. So the mass is low, density is low. And viscosity of a gas is become very thin. Just like imagine between you and the next person, there's a 1 mile between you guys. A lot of things can run through. Another property is gases are miscible to each other. Just remember, between you and your neighbor, there's a 1 mile distance between them. It doesn't matter to add a couple of other animals like squirrels, chickens, right? So since they're just too far away from each other, so it is okay for those gas particles to mix, or different gas particles to mix with each other. So those gas particles are miscible, means they can mix in any ratio, and they all share and occupy an entire space. This statement becomes quite important for us to understand one of the gas law later on in this lecture. It took a while for people to realize gas as matter. One of the evidence of a gas being matter is gas can have pressure. According to physics, pressure equals to force exerted on a certain area of the substance, force divided by area. What is the force? Where does the force come from? The air, right? So one thing that we can think of is the gravity, because we've got a lot of air above us. So gas particles, because they're matter, they have mass. So all their mass accumulate each other on top of each other. So all the mass that we have on our body becomes the pressure of the air. It is Torricelli who realized and measured the air pressure, or we call it atmospheric pressure. So he realized the 1 atm one atomic spherical pressure is about 760 millimeters mercury. And a couple of years later, Pascal in French picked up this research, and he studied very well enough about how the pressure is going to be measured and how the pressure can be explained by the mass of the air. And later on, he realized that the pressure changes with the height. So for example, pressure drops down quite a bit if you stay in the Alps country like Switzerland. So that is the reason why in Denver, a mile-high city, the pressure is only about 84% of the pressure that we have here in Florida. Because its contribution of the work in atmospheric pressure, we named a SI unit of pressure after him, Pascal. So 1 atm stands for atmospheric pressure is equal to 760 millimeters mercury. So here I want to put exact here, mean that is by definition. 760 is an exact number, which is also equal to 760 torr. Torr is a short for Torricelli, as you may realize. And in the SI unit, it is 1.01325 times 10 to the 5th Pascal. That's a lot of Pascal there. Usually we talk about the Pascal, we say in the unit of kilopascal. So we call it 101.325 kilopascal. But the more common unit we use in the industry is PSI, pounds per square inch. So that's roughly 14.7, and it equals to 1.01325 bar. That unit is usually used in the weather. According to physics, people realized in order to characterize gas, we need four variables. Variables like pressure, variables like volume, temperature, and amount of gas. So here, as you see, I labeled the units of these variables. You may realize during the pressure and volume, we have two sets of a unit for pressure and volume to use. As you see here, so for the pressure, if the unit of pressure is atm, the unit of volume must be liter. If liter use the volume for meters cube, pressure must be in Pascal. That two units comes with a set. It is very important for us to realize we cannot just pick any unit of pressure, any unit of volume. When we describe a gas, they must come from at least one of these two sets. Most commonly, atm and liter as the units of pressure and volume. For temperature, it must be Kelvin. Celsius, Fahrenheit are no longer available. When we describe the gas, it has to be Kelvin. So every time when you see the temperature in Celsius for the gas problem, convert that to the Kelvin right away. Gas we discussed in this chapter are the ideal gas. Ideal gas, by definition, is the particles that do not interact with one another at all. In order for us to understand that statement a little bit better, first we must say there's no attraction and repulsion between the gas particles. That is a very important statement for the ideal gas. We understand that cannot be true, because if we have time, we'll talk about the interaction between the particles. In other words, those repulsions, attractions between the particles exist no matter where they are, no matter how far they are, no matter how fast in their motions. However, in reality, we can approach this situation without absolutely eliminating those attractions and repulsion. We can put them in a very small scale, so compared to the regular gas, compared to the gas particles, so those attractions, repulsions become so small, becomes infinitesimal, we can ignore. For example, in order for attraction to become very, very small for gas particles, those gas particles must move fast. Why they must move fast? Because once they move fast, they themselves carry a lot of energy, so that the interaction becomes, compared to their energy, the energy they have, too small for us to consider. Another way to greatly reduce the reduction or attraction between the particle is to stay far away from each other. So these two becomes a very important condition for us to consider a gas being the ideal gas. Just how close a real gas should be considered as an ideal gas? These two conditions. In order those particles move or fly freely, there must be high temperature, at least 100 degrees higher than their boiling point, or the boiling point of a gas. So at a higher temperature, we'll guarantee those particles become gas. Once they become gas, they move freely and move very fast. Second, in order to guarantee those particles stay far away from each other, even in a gas state, we keep the low pressure. Remember, the greater pressure, the closer those gas particles will become. So let's keep the low pressure so these gas particles can just stay very far away from each other. In this way, attraction repulsion between the gas particles becomes so infinitesimal they can be ignored. So these two conditions becomes important for us to simplify the real gas problem into the ideal gas problem. If we consider air around us, air is an ideal gas because the room temperature is at least 250 degrees higher than the boiling points of any gas that we have in our air. And second, the pressure is low. It's about 1 atm. In order to have a gas, being a real gas, the pressure, as you can see, must be at least 100 atm or higher. That means 100 times more pressure that's on top of us, if we really consider air as a real gas. There are many gas laws in the history of science, all the way back to Boyle's law. I think that's somewhere around 15th century. But here, we only pick up 3 gaseous laws, like Boyle's law, Charles' law, and Avogadro's law. Boyle's law tells us if you have a pressure and a volume in a gas, the multiplication between the two winds up with a constant. I just want to remind you, there are 4 variables in order to characterize a gas. Pressure, volume are only 2 of those. If we focus on the pressure and the volume, their relation, that means the other 2 must be kept fixed. So the temperature must be the same. There's no leak in the gas for us to study. Since no leak, moles remains the same as well. Second law is the Charles law. It states the volume is directly proportional to temperature. In other words, as the temperature increases, volume increases, showing a linear relationship. Two variables that we are interested here in the Charles law, that means the other 2 must be kept fixed. So for the Charles law, in a system that under the constant pressure without any leak, volume is directly proportional to temperature. For Avogadro's law, in a container where the temperature and the pressure remain constant, the volume increases as the amount of gas increases. Or the volume is directly in proportional to the amount of gas the system has. Of course, there are more gas laws in that matter, but we only pick 3 because from these 3, we realize the volume is a function of the other 3 variables. For example, if we divide the pressure on both sides, V is equal to K1 over P. K1, K2, K3 are the constants. And we just copy down the other 2 laws. V is equal to K2 times T, V is equal to K3 times N. And we soon realize since the volume is directly proportional to all 3 of those, and one of it is the pressure is 1 over pressure, and they are directly proportional to all the 3, we can actually put all 3 together to have a V represented. And since K1, K2, K3 are the constants, multiplication of the 3 winds up a constant as well. So we can rewrite PV equals to NKT. We put a K between N and T. That definitely reminds some of you guys, because PV equals to nRT is what we call ideal gas law. You see how similar those two equations is PV equals to nRT, PV equals to PV equals to NKT. All we have here to do is to switch K with R. Remember, K is a constant, R must be the constant as well. And R is called the universal gas constant. And I want you guys to watch the unit of this universal gas constant carries. If we have a unit of liters and ATM, the value is 0.08206. If we have a unit of pressure and volume in SI unit, which is Pascal and cubic meter, the value here is 8.314. So it is very important for us to watch the units, especially for pressure and volume, because different units of this pair wants a different number of the R value. Okay, now that we know PV equals nRT, that a single equation put all four variables of gas together. Since there are four variables, according to math, if we fix three of them, the fourth one is fixed as well. In this way, we propose a special condition for gas as STP, standard temperature and pressure. Since temperature and the pressure are standard, the values of temperature will be 0 degrees Celsius. Remember, we cannot use Celsius for gas equation. 0 degrees Celsius equals to 273.15 Kelvin. The pressure under this definition, standard pressure and temperature, is 1 atm, 700 torr, or 760 millimeters of mercury. Remember, there are two variables are fixed, right? So we got the temperature fixed and then we have a pressure fixed. If we have the third variable fixed, the fourth is fixed as well. In order to make a third variable fixed, we called molar, means 1 mole. The standard molar volume of a gas, according to the equation PV equals nRT, now we'll solve for V. V is equal to nRT over P. As we put those values in along with the unit, remember, if we want to use the equation, we better put the units along so that we can cancel the units by keeping the one we want. As we can see, the ATM cancel, Kelvin cancel, ATM cancel, moles cancel, so we wind up with liters. The calculation tells us a molar volume equals to 22.4 liters. Molar, meaning mole. Liter, another unit. So this statement soon becomes to a conversion factor in our calculation. So the correct format for us to use this conversion factor is at STP, standard temperature and pressure. 1 mole of any gas equals to 22.4 liters of any gas. Of course, you can use PV equals to nRT to calculate it out. But I would like you guys to memorize this statement, this conversion factor, because this becomes quite handy. Once you see STP for gas, 22.4 is the number for liter as a volume if we have 1 mole of gas around. So this is a very convenient conversion factor for us to use. Here I give you 3 examples of these gases. As you can see, if they all have same 1 mole, 1 atm, and 273 Kelvin, they all have 22.4 liters. regardless of the identity of the gas. PV is called nRT is for a gas under one set of variables, always set in one condition. R here is a constant. That means if we move N and T to the other side by the division, we have a PV over NT equals to R. That becomes quite interesting. What's interesting here is that R is a universal gas constant. That means regardless what condition and what identity of the gas, they're always going to be R if we organize those four variables in this way: P times V divided by N divided by T. So that leads one question. Say if I have a same gas, but with two different conditions. According to what we have just discussed, P1 V1 over N1 T1 equals to R, and if a gas in a different condition, then we should have P2 V2 over N2 T2, because they both equals to the same number or a constant we call the universal gas constant, so we can ignore that part and put these two all together. This is what we call the combined gas equation. I'd like to point out that the internet version of combined gas equation is P1 V1 over T1 equals to P2 VT over T2. That is not complete. This equation, if we look at the one in the black with the one in the blue, our version, we notice that N is missing. N here is the moles of a gas. In this way, we can get this equation, the one in the black, under the assumption N1 equals to N2, meaning the moles of a gas doesn't change. That could be changed. So that is the reason why this equation in black, internet version, is not complete. It is my recommendation that we do not use that. Because if you do, if we have a question with the moles of a gas changes, we're going to have a problem answering it. All right, now let's talk a little bit about this combined gas equation, because this equation is unique. It has two sets of four variables that we need to sort out. So as a strategy, first thing we need to do is we lay out the information. We lay out the information, sort out the information, which one variable is belong to condition 1, which one is condition 2, which one is condition 1, which one is condition 2, and what is even more important is to find out what variable actually is held in constant during the change. Remember the previous discussion, we said N1 equals N2 for the internet version of combined gas equation. That is the one set of variable that is held constant. So that requires a lot of sorting and analyzing on the information the problem provides to us. Once we get those information sorted out, we also need to perform some necessary conversions. For example, we need to convert temperature to Kelvin, volume to the liters, while the pressure to the ATM. Remember, liters ATM comes with a set. And we need to convert the amount of a mass from mass or number of particles to the moles. Then we can rearrange this combined gas equation so that we can solve the problem. One thing I'd like to remind you, there are total 8 variables in 2 sets. We need to know the value or the relation among those variables, at least for 7, in order to solve for the last variable. And again, I'm going to put the calculation problem later on in the second half of our Chapter 10 discussion. Another gas law is called the Dalton's law. The full name of Dalton's law is Dalton's law of partial pressure. This is the law regarding the mixture of gases. It states in a mixture of unreacting gases, the total pressure is the sum of the partial pressure of each individual gases. All right. According to that law, we can write it into the mathematic form. So the P total is equal to the partial pressure of gas 1 plus the partial pressure of gas 2 after we exhaust all the gas in the gas mixture. Mathematics tells us it's a sigma. Sigma means sum. Sigma of Pi. I indicates each individual component gas in this gas mixture. This is the only law that deals with the gas mixture. So this law is clear enough for us to use when we realize this problem is about a gas mixture. In other words, gas mixture becomes the key word for us to realize this type of calculation, the calculation that will involve Dalton's law. If there is only this equation for Dalton's law is pretty much nothing, because that is only the very simple addition, right? So we know the partial pressure for each gas, and we add them all up, so we can have a P total. Or vice versa, if you know the P total and the partial pressure for the rest of the gas, so we can figure out the partial pressure of this gas, the gas the question wants. But that's not the point. The point is there's a lot more equation for the Dalton's law. Okay, so what I'm going to do here is try to reveal what other equations that's associated with Dalton's law make a Dalton's law one of the most confusing gas law ever in this chapter. Remember, when we talk about a gas mixture, for example, air inside our room, we understand air is a gas mixture, right? It has nitrogen, oxygen, carbon dioxide, water vapor, and the organic gases. So we can think of 4 different types of gases. But no matter which gas, they all occupy the entire space of the room, and they have the same temperature, because the room temperature is controlled by air conditioning. So what I would like to say here is, for each component gas, it has same temperature and volume as the gas mixture. All right, so with that in mind, remember, so for the gas, each gas, just like remember the analog I put between you and your next person, there's a 1 mile distance between you. So it doesn't matter if you have a couple of person right in the middle of this, because there's a plenty space for all of us. Same logic applies to the gas mixtures. Since those gas particles are so far away from each other for the same type of gas, so it doesn't matter if we have some other type of gas molecules or particles located between them. Remember, for each component gas, it occupies the same volume, has the same temperature, which means for each component gas, it should follow the ideal gas law. Because in terms of gas particle for same type of gas, they still have the certain distance, a long distance between them, like 1,000 times of the size. Remember, those gas particles do not have interactions. In other words, gas A and gas B do not have interaction, right? So when we talk about only gas A, the distance between the two particles of gas is 1,000 times of their sizes, so it doesn't matter. For gas A, it's an ideal gas. So gas 1, for the ideal gas law, P1V equals to N1 RT. If we divide both sides by volume, so we can have P1 equals to N1 times RT over V. And for gas 2, same argument, P2 equals to N2 RT divided by V. And we can apply that to P3 for the third component gas, on and on and on. So the first equation, that equation in green, our slide, should be rewritten as, after we substitute P, the partial pressure, with the formula here, would be P total equals to N1 RT over V plus N2 RV over V plus N3 RT over V, on and on and on. So here's the mistake. So it should be N3. It should be N3. But if we consider the gas mixture itself, like we said, if we have ideal gases as component gas all mix each other, ideal gas mixture is, of course, ideal gas. If it's ideal gas, it follows ideal gas law, PV equals nRT. Only this time, we use N total for the total amount of gas mix in this gas mixture. So N total times R times T over V equals to P total. When we see that equation, it's obviously we realize if we multiply V over RT on both sides, so the RT cancel. And if you multiply volume on both sides, V and V cancel. This is what we have left. N total equals to N1 plus N2 plus N3, which is equal to sigma Ni. So from P total equals to P1 plus P2 plus P3, then we derived N total equals to N1 plus N2 plus N3. This is the first equation we can derive from the Dalton's law. There is more. From that N total equation, if we define a new concept called the mole fraction. So mole fraction of a gas I, whatever, so just gas number I is equal to X of I equals to Ni, the moles of this gas divided by N total. Let's see what happens if we want to use this definition. Say if we divide both sides of the equation by N total. So N total divided by N total equals to N1 divided by N total plus N2 divided by N total plus N3 divided by N total, on and on and on. And of course, N total divided by N total, we want that with 1. For N1 divided by N total, according to the mole fraction definition, that's X1. So this is another equation we get. Meaning when we add the mole fractions of each gas together, there should be 1. Because when we add the moles of each gas all together, that's N total, right? N total divided by N total, according to the mole fraction, that is equal to 1. We are not done yet. According to the definition of this mole fraction, for gas number I here is equal to Ni divided by N total. If you remember, P total is equal to N total times RT over V. And for the gas number 1, we can easily replace gas number 1, the subscript into the I if we want to. So Pi equals to Ni times RT over V. These are the two equations that we have established on the previous slide. And of course, we can replace Ni, N total with these two equations. In other words, if we multiply RT over V, top and the bottom of this term, RT, if we divide by RT cancel, so V and V cancel. So according to mathematics, if I have Ni times some on zero number N total times the same non-zero number. These terms cancel. So mathematically speaking, it doesn't change. But in chemistry, it changes because Ni times RT over V is equal to Pi. N total times RT over V equals P total. So Ni over N total equals to Pi over P total, which is equal to the mole fraction. And of course, if we multiply P total on both sides, we have another equation. Pi equals the mole fraction times P total. All right, so from this discussion now, we have discovered few more equations like N total. From the definition of mole fraction, we find out that the Pi over N total, P total equals to Ni over N total equals to Xi. And if we multiply P total on both sides, so we have Pi equals to mole fraction of this gas times the total pressure. So how many equations we now have? 1, 2, 3, 4, and 5. 5 equations. So that makes Dalton's law the most confusing calculation problem of all in this chapter. And I'd like to stress this one more time, or emphasize this one more time. The key word for us to use Dalton's law is, right, mixture, gas mixture. And among all these equations, I just want to point out, when we realize this is Dalton's law, we always start with the equation of N total. So this is the layout of our strategy. We figure out the moles of each component gas so that we can have N total, then we deal with the rest. And we soon will see that in our second half of our lecture, which is the math. Another math problem we're going to see is the gas stoichiometry. Remember, when we talk about a reaction, we say A and B yields AB. If, say, both reactants are gases, we understand according to stoichiometry, we can link the moles of gas A with the moles of gas B using coefficients as a stoichiometry. Now that we know both A and B are gases, so we understand N equals to PV over RT, and we can extend that solution map into this. Remember, this is what we have from stoichiometry, and these are the new ones. PVT of the gas B or PVT of the gas A, because PV over RT is equal to N. So here we use the gas law as the conversion factor. Itself is a mathematical equation. Remember, in the beginning of the chapter 4, we said another form of conversion factor can be equation, right? So if we use a PV equals to nRT, then the equation as conversion factor, we can convert the moles into either P or V or T if other variables are given. So here are the conversion factors. Molar ratio from stoichiometry between the moles of different substances, as we already discussed. And we can use ideal gas law to convert the moles into whatever the variables that question wants or question provides. And now let's look at this solution map. Remember, in chapter 4, I said this solution map covers pretty much every stoichiometric question that we're going to see in Chem 1 class. So grams, moles, moles, grams, that is something that's very commonly seen in chapter 4. Sometimes we see number, moles, moles, number, or any other conversion. So this is what we see in chapter 4. And leaders after we introduced molarity. And heat is something that we discussed in chapter 5, right? It's a heat reaction. So if you have a thermochemical equation that involves heat, and we consider heat as a reactant, so we can have a mole related to the heat. Now, another branch, PVT to the moles, then moles to the different substances to the PVT of the second substance. This is some solution map that we're going to use when we have a gas involved in the stoichiometry. All right, now that we have talked about a whole bunch of gas laws, right? We have 3 gas laws: Boyle's, Charles, and Avogadro's. From those 3 laws, we derived ideal gas law. From ideal gas law, same gas with a different condition, we have a combined gas equation. Some people will call it combined gas law. And from that, we talk about Dalton's law, and Dalton's law comes with a whole bunch of equations, not just one. Although the law says P total, but we have N total as well as mole fractions. So Dalton's law comes with a lot of equations. And of course, we have just discussed stoichiometry among the gases. Among all these laws, we need a model or theory to explain how this law works and why this law works. From the very beginning, we understand gas have these property as we call the macroscopic property. Right, so we have so gas can be compressed, gas can be contracted, low viscosity, low density, and miscible. But among all of these four variables, all of these variables, there's one thing that puzzles people the most. Let's think about it. Most of gas, just like most of a solid or liquid, we can measure, there's no problem. Temperature, we can measure it, right? Volume, the size of a room, so it can be measured. What about pressure? Of course, pressure can be measured. But pressure puzzles people the way is slightly different from solid or liquid. When we say if a solid or liquid has a pressure, we usually consider the pressure of the substance that's underneath the liquid or solid, right? For example, if we stand on the scale is underneath us, so scale feels the pressure, convert the pressure into the mass or the weight, right? So we know just how much we weigh. But for gas, it's special. If we have a gas in the room, actually each dimension should have the pressure. So gas put the same pressure on the floor as it does to the ceiling. That makes people puzzle. How does that work? There got to be some kind of explanation that explains why gas can have a pressure on the ceiling or the 4 sides of the cube of the room, right? Except for the floor. Why? So with that in mind, around 1880 to 1900s, 2 scientists did the research simultaneously in 2 different countries. Maxwell in Britain, Boltzmann in Austria. They didn't know each other. They heard about it from each other, but they didn't see each other face to face. So they started their research in almost the same time for the same topic, try to explain the behavior of the gases. They both came up the exactly same mathematical approach, which is we called statistical thermodynamics. According to this model, they said this model that we deal with huge number of particles, not just each individual particle. Before this moment, when we say something, when we say box, that's one box. When we say the reaction, that's one molecule or one atom, so on and so forth. For mathematics, we say 1 mole, but we still refer that as one reactor individually. But when we deal with a gas, we have a different mathematical approach. We talk about the general behavior as the population of a gas. Each gas has its individuality, but as a society, we can find some common clue or common pattern for those gases. So statistical is a math. The statistics is a math that deal with something that's in a large number. Millions is even smaller. In this chapter, we talk about trillions of trillions. Remember 10 to the 23rd for 1 mole of a substance. So when we deal with this many of particles, we need to simplify something. So here's the things that we simplify. We say gas molecules or gas particles, they do have a mass, but they do not have a volume. Why they don't have a volume? Because if you have the volume we use for the gas is not the entire volume for the gas to occupy, right? Because gas cannot go to the inside of other gas to occupy the space. So let's eliminate that. This complicated problem by saying gas has no volume. Second, gas does not have attraction in between. We understandable, that's what ideal gas is for. When gas moves, remember gas moves in very fast speed, just like a bullet train or the bullet. So they move in constant random straight line motion before they collide something. For example, the wall of a container. We just said they had no volume, right? Because for each gas particle. But what happened? Say 1 of a billionth, they collide. Just point to point, they collide to each other. So once they collide with each other, they follow the law of conservation of energy. So that means the particle can collide with the conservation of energy. These two particles, before collide, has certain energy. After the collision, those particles, when we added their energies together, it's the same. Even though each gas particle may have a different energy, but when we add these two together, they still follow the law of conservation of energy. So these are those hypotheses. If we follow those hypotheses, we can actually calculate the average speed of the gas particle. That's U, bar in mathematics, average, equals to 3RT over molar mass. MM stands for molar mass of the gas. I just want to point out 3 is the number, R is the constant, T is the temperature, divided by molar mass. If we know the substance, we know the molar mass. So the energy can be used to define temperature. Remember in chapter 5, when we talk about the end, so temperature is related to the certain motion of the substance. Here is the math. Temperature can be defined by how fast the substance moves in average. Nevertheless, from that equation, we can come up with a conclusion saying the less the molar mass, the higher the temperature, the faster the particle moves. So that is why hydrogen gas particle moves the fastest. Okay, so hydrogen gas moves almost, I cannot say 10 times, almost 3 times as fast as the speed of oxygen moves in average. So this is how much of the difference there. And also, from that equation, if you're interested, you should be able to calculate just how fast those molecules moves or particle moves. Rule of thumb tells us those molecules moves in the speed of few hundreds per second. Okay, so that is why it's okay, few times more than the speed of the sound. Okay, now let's try to understand the pressure using this theory. According to this kinetic molecular theory, in short, KMT, we need to understand, so those gas particles are in constant motion, right? And as we already described, how fast those gas particle moves. With a speed of 200 meters per second, for example. In a small room, those gas particles bounce the walls back and forth probably 100 times in a second. Not only it can bounce left to the right, it can also bounce upside down and front and back, 3 dimensions. Now suddenly the pressure of a gas in all dimensions of a room which can be measured makes sense, because we have gas particles move or flies all the time, bouncing back and forth against the wall of the container. It doesn't matter what wall, because gas molecule particles bounce upside down, so it gives the pressure top and bottom. Left and right, front and back, gives the pressure for the rest of the walls of a container. So the pressure actually can be considered as how many gas particles are doing the same thing, right? Bounce back and forth on the wall. And also, it depends on how strong or how fast those gas particle moves. For example, the gas particle moves just like 80 meters per second. Gas particle moves like 400 meters per second. They definitely have different energies. Since they have different kinetic energy, and then, so when they hit on the wall, they can have a difference, okay, in terms of pressure that we measure on the wall. Remember, just like we play with the drum, if we tap the drum, so we hear a certain sound. The sound is a reflection of the pressure that we have on the membrane, right? So we hear a certain sound. But we also can hit the drum, right, with a greater force. And of course, these are the 2 factors that we can consider as a source of the pressure from the gas particles. In this way, we put in a simple math on top of it to say it's just simply directly proportional to how frequent and how hard the particle pound on the wall of a container. That is what the pressure is. How frequent can be explained as the density of the gas. Density, mass divided by volume. Mass can be converted to the moles. Moles can be converted to the number of particles in this way. So density represents how frequent those particles hit on the wall to generate pressure. On the other hand, remember, temperature determines the speed of the particle. So the higher the temperature, the faster the particle moves. The faster the particle moves, the harder the pounding, the greater the pressure. Now that we have a pressure explained by the motion of particles hitting on the wall, we can actually explain pretty much all the gas laws that we have discussed. For example, Boyle's law. Boyle's law tells us as we push the gas into the smaller volume, we feel more and more pressure. So that's why P times V equals to a constant. Now let's think about it. As we pressure this piston to the smaller volume, as in this case, now we see the volume has decreased. Same amount of gas, meaning same number of gas particles. Since the volume is reduced by the factor of 2, for example, the density of a gas is increased by the factor of 2. Remember, pressure is directly proportional to how frequent, in other words, the density of the particles pounding on the wall of the container. Density increased by the factor of 2, the pressure inside doubles. Since the pressure inside doubles, we feel the resistance. So we feel the pressure inside gets higher and higher, requires us to push harder and harder down in order to reach the volume we want. That is what the Boyle's law is. As volume decreases, pressure increases. Or vice versa, as pressure increases, as volume increases, pressure decreases as a result. So the Boyle's law can be explained by the KMT theory easily. Now, let's look at Charles' law. Charles' law tells us as we raise the temperature of the gas, its volume expands. Linearly, of course, it's a direct proportional, right? Let's consider that in 2 steps. First, we increase the temperature of the gas. Remember this equation. As we increase the temperature of the gas, speed increases. So the speed of a gas particle increases. Speed of a gas particle increases, meaning it's more energetic. Gas particles more energetic results the greater pounding of the gas particle on the wall. Greater pounding meaning the higher the pressure. Once there's a higher pressure inside, in order to keep up the pressure, less pressure outside, the volume expands according to the Boyle's law. So the Charles law can be easily explained by the KMT theory too. Okay. All we have to do is add one more step, apply. So once we analyze it, figure out the pressure, and then we use the Boyle's law to explain it, why the volume expands. Because the pressure of inside must be equal to the outside in order for us to assume, to observe this Charles law. So it has Boyle's law at the end. Avogadro law is much easier to explain because we are pumping gas particles as we increase the moles of the gas. As we increase moles of gas by adding more and more gas particles into this volume, more gas particles, the denser it is, the greater pressure it is. Again, using Boyle's law to explain why the volume expands. Because before and after, that's the same volume, right? Or same pressure, right? So if the pressure inside is greater, the volume expands in order to meet the pressure that's outside. So Avogadro laws can be explained as well. The last law I'd like to explain using KMT theory is a Dalton's law. Dalton's law, one way to put it is, okay, so if I have gas A in that gas cylinder, now I'm pumping another gas into that gas cylinder. One way to put it, we increase the number of gas particles. By increasing the gas particles, according to Avogadro's law, the pressure will increase as a result. Right? That's what Dalton's law is. But what we want to explain more carefully is how come this partial pressure is corresponding to this type of gas. That is something that we need to associate that type of gas with its partial pressure. Because remember, Dalton's law is about partial pressure, P1 plus P2 plus P3. How do we know P1 is for gas 1, P2 is for gas 2? In order to explain this, I just wanted to look at this equation but from different aspects. Here, the average speed of the gas particle is also the function of molar mass of the gas. We understand different gas has the different molar mass. And since gas has different molar mass, they must have a different speed, right? If they have a different speed, they hit the wall with a different hardness. Different hardness can be explained by the different pressure, which is the partial pressure of each gas. So that is why P total is not simply just we add those N1 plus N2 together. It also explains P total is equal to P1 plus P2. One last behavior of the gas or the property of the gas is effusion and diffusion. Effusion, according to the definition, is a gas escape a container to this evacuated absolute vacuum space through the pinhole. And it was the British discovered this behavior, and he says, and of course that's just the law, he says the rate of effusion of a gas is inversely directly proportional to the square root of its molar mass. In mathematics, the rate is, this is what's said, directly proportional to 1 over the square root of a mass. And what's the diffusion? Diffusion is, if you have a gas A here, and here you put another gas B here, and to gas B, this side is absolutely vacuum because no gas particle there. For gas A here, this is absolute vacuum, so they fuse each other. So diffusion is the application of effuse. So once we understand effusion, we can explain diffusion easily. But can the effusion be explained by the KMT theory we have just discussed? So here, remember, we have an equation. The equation here tells us the average speed of the gas particles is equal to the square root of 3RT over molar mass. According to math, the square root of the division is equal to the square root of each term in the division. So square root of 3RT over the square root of a molar mass. At a constant temperature is a constant, R is a constant, 3 is the number, so the top is a constant. Now we realize the rate of effusion is kind of like at the speed of a particle that moves, directly proportional to 1 over the square root of a molar mass. Well, just how about if we have second gas? So say we have a gas A here, and also we have a gas B here. So we have two gases that's sealed on the right-hand side of this box, and we put a small hole, the pinhole there, to see how fast they can infuse. In order for us to talk about the fusion between the two gases, grams gives us this equation. The rate of A over rate of B is equal to the square root of a molar mass of B divided by the square root of a molar mass of A. And of course, as you can see, according to that equation here, the gas with a different molar mass will infuse in a different rate. And this is exactly, we can have another part of Graham's law of diffusion. So we have two gases because they infuse in a different rate, and this is what we have. One thing I'd like to point out here is rate of A over rate of B is B over A of their square root of molar masses. So that is a cross, as you can see, right? A cross, so again A here. There's a B cross that's going to be on the top. This concludes the first half of this chapter. So in this chapter, we talk about the concepts, we talk about the laws, and we talk about the models or the theory that explains all the gases laws. Right? So in our second half, we're going to talk about the math of this chapter, which is more confusing than the chapter itself.